Our speaker today, Eric Erslev, drove up today from Fort Collins. And Eric, I should say a few official things rather than just talk about drinking with students and things like that. But Eric has a bachelor's in geology from Wesleyan University and a PhD from Harvard University. He was an assistant professor at Lafayette College, assistant associate full professor at Colorado State University, and since 2009 he's been emeritus at Colorado CSU and adjunct professor at the University of Wyoming, which is where my connection with Eric comes from, because I was aware of Eric as a structural geologist, which any structural geologist who has any interest in the western U.S. in compressional tectonics, how the world is put together that way, knows of Eric amongst other outstanding structural geologists. And that is his field of expertise, and in particular, though, the Rocky Mountains. And what he's going to talk to you about tonight is about how this country that we live in and that we know and I think love, all the way to the Nebraska border, actually was farmed. And so I won't get off into drinking stories, and without further ado, I'm going to turn the floor over to Eric Erslev. Please welcome Eric.
I got to figure out how to
unplug the one. Get back to yours.
I am really impressed at the number of people such a small community can come out and be so interested in how the Rockies form. For me, it's always been a huge puzzle to me. It's been a huge motivator. Started looking at the Rockies from Gannett Peak when I was 17 and climbed up there with a good family friend who had broken the Knowles age guideline by being 4 years older than their oldest permissible person, and as a result, they eliminated the guideline totally. Took some time off from Wyoming, was out east for quite a while, and then got the opportunity to apply for a position at CSU. I arrived a little bit early, and my host said, "Hey, let's go down and hear Don Blackstone, eminent structural geologist from University of Wyoming, talk," and he gave me the biggest gift I've ever gotten. You see, he came up, he strode out on stage, probably about 75 at the time. He said, "I've got 3 things I want to tell you. First, I am not a candidate for your position." That was good news for me, because I was what I was after. Second, he pointed to a colleague, soon-to-be colleague of mine, said, "McCallum, you're getting fat. Get out in the field." He said, third, this is the type locality for vertical tectonics. Doesn't work in Wyoming, or rather in Wyoming. It shouldn't work here. Get off your duff and figure out what's going on." And thus I had a whole career worth of work gifted to me at my job interview. The work I want to present today is the result of a big project, NSF-funded Bighorn Project, which was part of the EarthScope program, which looked at the entire geology and structure of the continent of North America. It's still in progress, currently scanning through Alaska. We also had funding from the Air Force and from IRIS and the W.M. Keck Foundation, which is an undergraduate foundation. And our big project was trying to figure out why basement involved foreland mountain belts, so things like the Wind Rivers, the Bighorns, why and how they form. A big puzzle because it's so far away from plate boundaries. My principal investigators who worked with me, Ann Sheehan, Kate Miller, Megan Anderson, those are all seismologists. Christine Sidaway, she's another structural geologist, someone who talks about faulting, folding, deformation of rocks. And it's been a fascinating journey. from figuring out how these things work, which then reveals why they're there to start with. So it turns out that the whole Western Americas are characterized by these big mountain belts, compressional mountain belts, such as what we have to the west, what we call a cordilleran origin, right there as well. And every once in a while, you get areas where the basement, the craton itself, is rocked up into big folds and faults. These are what I call basement arches. And they've been a real puzzle. Problem is that the plate boundary's out here, so it's quite a ways away from the actual mountain belts themselves. And it's very important because how these form will determine seismicity in places like the Sierras Papianas, which is active today, and also earth resources, like the current resource plays, which are critically dependent on fractures due to mountain belts like this. So I'll be talking about how the Rockies rose from the sea from about 70 to 50 million years ago. That was during the Laramide Orogeny, and how they were related to plate tectonics. You can see some of the folds here at Rainbow Canyon on Rattlesnake Mountain. Also a big fault. It's actually a normal fault, but it's only 5 degrees from vertical. And the problem is that these basement rocks, these crystalline rocks, which form the cores of many of the mountains in the Rockies, sort of to the east and south of here, are very heterogeneous. They're not like the layered sedimentary rocks. But what we have determined is that with seismic, well, and fault data, these are clearly thrust origins with big thrust faults, which over where the basement rocks, here we have 3 billion-year-old rocks in the Wind Rivers, on top of 100 million-year-old rocks, which were thrust over. In our analog down in Argentina, this is in the Sierras Papianas, we have these little basketballs. You just take my word for it. These little focal plane mechanisms, as they're called, tell you what kind of fault they're. And these are characteristic of thrust faults. Now before, a lot of people talked about vertical tectonics. They saw the Rockies as a bunch of pistons with the mountains up, like between the two small blocks, and the basins down. Problem with that is we try to get this to move from the start. You can press on this forever, and that middle block's not going to move. Vertical tectonics just does not work. Whereas if you have a thrust fault, you can get thickened mountain belts, which is the characteristic of mountain belts, by simply just pushing slightly, and the crust thickens. It's higher. Now we've done a lot of work in this area. I've had about 40 grad students who are tirelessly collecting information on faults, on collecting information on where folds and faults are mapped. And when you look at these, you see a nice uniform east-northeast shortening or compression direction, which is perpendicular to the folds. The blue line here, which makes a lot of sense, because when you push on a piece of cloth, the fold develops perpendicular to the push. There were some ideas about having this be due to multiple stages and directions of push, but it's not really needed. Adolf Janke and Arlo Weil confirmed this by studies in Wyoming itself. Here, whoops, all right, hit the wrong button. Here's the cordilleran thrust belt, where you, for a long time, we've been able to see stacked up layers of rocks. Out here, it's been the question of whether these faults are vertical, strike slip, thrust faults, and what Weil and Janke did was show that layer parallel shortening and thrust faulting were pretty much seamlessly shared by the Cordilleran Thrust Belt and these Rocky Mountain basement arches. So the conclusion is that the Rockies, and this is sort of the how, are basically a thrust belt. And the question is, do they show the same sort of folding and faulting? Well, the faulting, definitely. The folding in a thin-skinned thrust belt, such as what's to the west of us here, we have faulting by detachment. So you slip on this layer and extra stuff slides up, sort of like if you put your hand on a tablecloth, push it forward and you have folds in front of it. And then you have faults which propagate upwards. It's called a fault propagation fold. And when you finally get a bent fault, you get folding over top. A lot of what I've been working on is trying to figure out how that works in basement. Those illustrations show it in sedimentary rocks, which have lots of layers to slip on. But basement faults and rotates as blocks. And thus, you can model it as a fault in basement, turning into folds in the cover. You can model the Wind River Arch very successfully as a rotational block with a curvature which takes this down to about 30 kilometers depth, where the fault goes horizontal. This is a restorable model. If you pull back all the faults, undo all the folds, it'll be a layer cake model for what we would say would be a general Rocky Mountain foreland arch. So just to review where we were prior to the Bighorn Project, we disproved the vertical uplift. There are vertical faults, but they're almost all strike slip. The multi-directional compression, we didn't see any evidence for it. We measured a lot of stuff to try to find it. One of the thoughts, which has been very current these days, is that we have some sort of shear on the base of the North American continent, on the base of the lithosphere, which is the upper mantle and the crust. But what we have shown is that the Precambrian mantle is in place underneath the crust of the same age. So there hasn't been any big shear going on at depth. So the conclusion 7-8 years ago was that we had some sort of compression from the west, from the Cordilleran Thrust Belt, which is what's west of us here. And you have these 4 different models, which probably could be better seen in cartoon form, where you either have big lithosphere cutting faults, we have bulges, which bulge downwards underneath each arch. We have detachment, which I'm biased for. I did publish on this, just in the geometry. And then we have lithospheric buckling, where we have the whole lithosphere buckle up and down. So those are the 4 major hypotheses we were going to test. The problem with these hypotheses is that what we can see at the surface can be pretty much the same, but what's at depth is quite different. So we picked the Bighorn Arch, had the least amount of previous deformation. This is the topography here. It has nice access through roads for both ends of the arch. This diagram on the right side here is actually the elevation of a 10-sleep formation, which is pretty well documented by well data and seismic data. It's about 1 kilometer above basement, with the reds being the highs, the blues being the depths. And so here you have what I call an arch, a number of arches coming together, and basins on either side. If you take a profile through the Bighorn Arch, here this is from Don Stone, huge amount of seismic data, well data, outcrop data, and you apply those 4 models, they predict very different moho geometries. Now, me as a structural geologist, this is inaccessible. That's why we need seismologists. And then we've got a whole bunch of seismologists. So again, I've highlighted in yellow. Oops. Oh, I'm going the wrong way. There we Highlighted in yellow, some of my colleagues here, the other PIs. Here's Christine Sidaway, another structural geology, Megan Anderson and Sheehan, Kate Miller, right there. Those are the people doing the seismology. They actually got the big money because their stuff costs a lot of money. I just need a couple extra pairs of boots and some computers every once in a while. What we ended up doing was instrumenting a whole series of profiles parallel to and perpendicular to the bighorns. What looks like red lines is actually individual dots showing placements of small seismometers. The blue and the black and the triangles are larger seismometers. We had two types of basic studies. One is a passive, which is using a distant earthquake as an energy source, and an active, where we set off explosions in places which have been disturbed previously, old quarries and things like that. The end result is much like a CAT scan or an ultrasound of a baby in a mother's womb. We got to be able to see what was below the surface. So here I'll just skip through some of the instrumentation. We went from very large units, where we densified the US array suite of instruments across the US. And then we had smaller ones which came in for about 6 months. And then, very small, we just had this little computer in a box. Randy Keller, who was at Texas at UTEP at the time, basically made up this thing. He said, they're really small, and that's why he called them a Texan. And they're also, he said, they're really dumb, but I'm just quoting Randy. Okay, I'm just quoting. These are shorter term, so you can put those out, set off some blasts, and then pick them up. They're just decelled. But it's fun. If you ever get a chance to be on a seismic experiment, here, oops, there you go. Megan's waxing poetic about this larger scale unit, which went in for about 2 years. Here are some units I was putting in with a gal from the University of Puerto Rico, where we were just putting them in every 100 meters on a transect. What I'm going to show today is mostly stuff on line 1, which is right across here from Cody to north of Gillette, because that's sort of perpendicular to the grain of the bighorns, shows what's going on. In our passive source experiments, the primary method is what's called receiver function wave imaging. It's a bit of a mouthful, but what it is a distant earthquake goes through the earth, comes up, hits the crust, and spawns off an S wave. The P wave moves about twice as fast as the S wave, so the difference in arrival time of those two waves is basically the thickness, or is a function of the thickness of the crust. And this is an illustration of the receiver function data. We have some stuff which is just reflecting off the bottom of the basin here in black. And this is actually the moho. This is the basically the difference, or the contact between the crust above and the mantle below. What you can see is the moho is actually arched a little bit underneath the bighorns. Although the arch is very different in shape and form than this black line, which is the deformation in the Laramide. In fact, this one's dipping west, this one's dipping east. So we confirm that work with active source, where we basically put in a fertilizer bomb of 1,000 to 2,000 pounds of blasting agent in, once again, in a disturbed area. This is a raw active seismic data. Each one of these squiggles is a seismometer record in time from what was 0, which was the start, when the thing was set off, on. And what you can see is you'll see different reflections, different waves, which come up at different times because all the layers have different velocities. You can take that and create, here's our equivalent of an ultrasound of the crust. And in addition to that, we had off these white dots, which is where our explosions were, we had reflections off the moat. So this is interesting. It's confirming that the passive data here looks very much the same as the active data. These are slightly different scale. Okay. But they both don't really look much like the Laramide, which in this case is white. So we're wondering, so what's going on here? Is this really buckling of the whole lithosphere, or is something more going on? So that's where my group got in, the structural geologists. Karen Aidian, who's a master's student finishing up at Wyoming, is working on this right now, where we basically took a project in 3D, where we took the geology here, we added in the basement, or the top of the tensely, which is that surface I showed earlier. Now it's popping up where it's been eroded out, but it extends underneath these basins. This is the Bighorns right here. We can strip off the surface geology, and that's what these basement arches, Laramide basement arches, look like. Here's the Wind Rivers, Owl Creeks, Bighorn, Ertues, Bighorn Basin right there. Now we can do the same thing with the Moho, with the receiver function data. And we can stack it on top of each other, and you can't see anything. Okay, it's from Williak. But what we can do is take them apart, and just if you can register this, I need to do a little better job here, but this star is the same as that star, the scale is the same. This actually is more amplitude than this, but you can see that this geometry here does not match that geometry there. These are two independent things. If they're independent, what that requires is that there's a detachment in between. The lower part is probably Precambrian. That actually matches the Precambrian geology pretty well. The upper part, right here, is Laramide. So, everybody confused? Good, good, all right. Make sure so, how does detachment build mountains? So here what I've done is taken that 3D, taken a slice through it. It's actually Don Stone's original cross-section, okay, and brought in additional dimension of time. That's what structural geologists do. And so what I can do is restore that, and what we see is that will restore to something which is pretty close to flat. So that's actually a possible configuration. You can't do that with a vertical model. You can then see it come out of the seas by just doing a forward modeling of that. And you can see it folds for a while and then it falls. We can also do this on the line, which we did our line 1 in our seismic section. And we can have that thing restore as well. We can validate that this is a possible hypothesis. Okay? So, or at least not falsified. Maybe other ones. And then we can see it as it probably came out of the sea. So, a primary conclusion here of the how is that the Bighorn Arch was formed by lower crustal detachment. When you look at these predicted configurations, crustal detachment says it would be independent of the arch, and that's what we saw. How did it work in 3 dimensions? Well, to do that, we had lots of students out collecting faults. I like to call these the fault information. This is a big thrust fault. I like to think of these as geo-skid marks. Okay, that's basically that fault moved there, created a lineation, and that gives you an idea of where they're moving. Here's something which broke apart on Sheep Mountain. We plot all these up. We have some interesting patterns developing. In the middle of the range, I'm sorry, you guys, I'm sort of neglecting you over here. In the middle of the range, I'll come over here for a while. How about that? The yellow is the horizontal line on a fault. The red is the slip direction. And a fault like that, where these are perpendicular, means it's a thrust fault, because the horizontal line on a fault, on the fault, is perpendicular to where it's moving. In this area here, the faults are basically almost parallel to each other. What that means is we have high angle faults like the San Andreas, and they're sliding strike-slip, parallel to the strike. And the result is we have a fairly simple picture where you're just pushing on this crust, you're detaching, it's pushing out here with thrust faults, and on the sides, you're shearing a bit. You can do this in the snow. Push your snow shovel. You'll see the exact same thing with the thrust faults coming out in front of your snow shovel and tear faults on either side, strike, slip. Or you can do my version of plate tectonics here. Where here I'm taking this plate, taking this tablecloth, just pushed in, we create these arches. These are detachment folds, okay? And at the edges, you have to have some shear and strike slip. It's another way, which is a little bit harder to wrap your mind about, but we've got all this three-dimensional data. So what we can do is run a whole bunch of different profiles through, there's the Bighorn arch. And you can actually use space as a proxy for time if you presume that where the arch is very small, that was an early stage of deformation, whereas where it's really big, that's a late stage of deformation. So this would be an early stage of deformation just south of Billings, where you just have a little bowing up. You probably have a little bit of deformation thickening the crust right there. And then it gets a little bigger, you get some little faults coming in here, breaking up the surface. Then we get faults going the other way. Perhaps these are pre-existing weaknesses which are reactivating, different geometry. And finally, a bigger fault, which is what's right in between Sheridan and Buffalo. So this is the sequence of deformation we see in the basement-involved thrust belt east of here, where you basically have shortening and fold thickening, followed by the breakthrough of a fault, big thrust fault, to create the culminations of the arches themselves. I think this works. What about the why? Locally, why are the bighorns where they are? Why are the Wind Rivers where they are? Regionally, why don't we have these basement-involved thrust belts to the east of the whole cordilleran section instead of in small patches here and there? Let's look at the local controls. We know that if you have weaknesses in the crust, that these will cause, someplace there, a difference in geometry. So this is a numeric model which I've been working with some people from Rice and Amoco, or not Amoco, Exxon. The colors in the upper part are actually the amount of deformation, amount of strain which is experienced. It's very similar in geometry to some of our earlier models. Down below here, we just have more a layered model. And what you can see, however, is that where you have no seated weakness, you get a symmetric arch. Where you are seated with a weakness, an old fault, you get an asymmetrical arch. And that's why the geometry changes so much, I think, in these structures. Why might the bighorns be where they are? What's the reason why? Well, it turns out that when we looked at the reflection data from our active work, we saw that right in this area here, we went from a transition from less reflective, probably granitic material, and more reflective material. And we're wondering whether that's a possible Precambrian shear zone or suture zone, which focus deformation there. We can see that aeromagnetically. This is the magnetics. It's flown over and recorded by a plane. What we see is right on the eastern side of the bighorns, which is right here. We go from these red, highly magnetized, positively magnetized, to negatively magnetized rocks. This is a big contact in the basement at depth, which you can't see on the surface. We suggest that that may be a major crustal boundary. In addition, we have to ask what happens with lateral changes in strength. One of the things, a previous profile, which is shown here in red, called the DPRO project, showed was that underneath Wyoming, we have this really strong, very fast layer, greater than 7 kilometers per second layer. And we were wondering whether that might control detachment. So when we did the gravity, and I'm sorry I'm throwing a lot of data at you, but this is a lot of stuff here. When you do the gravity and you get the interpretation, we find out that, oh, this is the DPRO line here with the 7x high-speed, probably very rigid material. Here it is on the other side near the Black Hills, and there's nothing where the bighorns are. The higher density it is, probably the stronger it is. This suggests that underneath the bighorns, we have weak crust. What happens when you get a gap in a layer which is weaker? Well, it turns out this happens a lot in thin-skin thrust belts, sedimentary thrust belts. Here are the Appalachians, where you went from Cambrian rocks here, which are mostly carbonates, into a big shale basin. And Bill Thomas had a very picturesque word for what happens here. He calls it a mushwad. So literally what you do is you're just pushing on it. It's really soft, so it just stacks on top of itself somewhat chaotically. Here's some of the material in it, and creates this great big arch. So this is all above basement in the southern Appalachians. This is probably what's happening down near the Moho in that weak crust underneath the bighorns. And I could talk a lot. We have all sorts of different possibilities here. We have the possibility that this is a suture zone between the bighorns, between the Archean, the very old Precambrian, and the younger Precambrian. And obviously we've got this gap in the 7x layer. We don't know exactly what's really controlling everything, but clearly the basement is not uniform. It's very heterogeneous. It's very heterogeneous. So finally, boy, I guess I'm talking fast. Must have had a lot of coffee today. Why don't basement-involved thrust belts occur in all cratonic formations of these big thrust belts? Here we go back to this slide here. Here's the Canadian Rockies. It's a classic thin skin, which means only sedimentary rocks stacked on top of each other, one after another after another. Huge amount of shortening, no basement arches out here. The basement is pretty much undeformed. Yet down here, we have basement arches developing very nicely, going way out to the Black Hills. There's the bighorns right here. Here we are right here, Jackson. Why is it we activated the craton here, but not up here? Or to the south in Mexico. where again, we have the same situation as Canada, where we have this big thrust belt and nothing happening to the basement. The one thing we know which correlates with this is that we do have a gap in our magmatic activity right around the Laramide. For the Laramide, we have the Sierra batholith, then it just cut off. And we think that's because this area of the Rockies underwent low-angle subduction. The subduction, instead of diving down steeply, went pretty shallow. That's currently what's happening in the Sierras Pampeanas down in Argentina, where we have a modern analog. We have these little triangles here on volcanoes, and this big magmatic gap. I didn't just cover them up. There really are none right in this area here. Right where the Juan Fernandez Oceanic Ridge, which is buoyant, is being subducted underneath the continent. And you can see that slab seismically because it has earthquakes in it, and it goes flat or relatively low angle right in the area of the Sierras Pampeanas, which are these big basement arches, just like the Laramide basement arches. This case is about 1/4 the scale, but it seems to be a parallel situation. So here's another figure which shows this. The magmatic units in black are before the Laramide. And that's the Sierra Nevada right there. The ones in gray are single Laramide. While we have a few things like the Colorado Mineral Belt, this area right here is pretty much a magmatic gap. And there's been a lot of work to say that this is caused by the actual subduction of an oceanic plateau, for which we can see the mirror image in the Western Pacific. The problem with using that as a mechanism, however, is it's actually gone by the time the Laramide starts. And we know that the idea of basal shear, so this big plateau rubbing against the bottom of the craton of the continent, doesn't work because the push is from the west, it's not from below. We know from all the fault work that a horizontal push from the west was needed, but clearly was not sufficient because it didn't cause basement-involved arches up in Canada, down in Mexico, throughout most of South America. So what could be happening? You could have heat weakening the craton, but low-angle subduction actually cools, called refrigerates the craton. It makes it stronger. So what the heck is causing these to become unglued? That leaves the one thing which low-angle subduction has, which is fluids. There's been a lot of work by Don Hinman and others about cordillera origins. Here we would be basically right on the edge of the Canadian thrust belt right there, where when you have normal subduction, the slab comes down, it gets down to about 100 to 200 kilometers depth, and up comes the water. It causes melting and weakening of the mantle, and we get a volcanic arc. And the result is that we get this very weak cordillera origin, very weak. This is the area right there. This is how strong. Weak strength is to the right here. Very weak back arc area relative to the craton, which is immensely strong. It's immensely strong because it's cool. This is temperature versus depth. Cratons are much cooler than mobile belts or back arcs. But what happens when you have that low-angle subduction, Claire Curry and Chris Beaumont has modeled this in detail. Here we have high-angle subduction. We have hydrous minerals, which are in these colors here, come down, lose their water, and we get an arc right there. We get batholiths. We get the Sierra Nevada. Okay, we get the Cascades. However, when it gets low angle, it pushes out the hot mantle, the asthenosphere, And these hydrous minerals go way the heck underneath 150 or 1,500 kilometers underneath the craton. That water is not going to be happy there. That water goes up into the overlying material. So what low-angle subduction does is it cools the mantle, but at the same time it hydrates it. How's that important? Well, it turns out that the Rockies, in terms of the areas to the east of here, are acting like a jelly sandwich. We know that the upper mantle is strong because we have these mountain belts, but there's no roots. You know, you always hear about mountain belts having roots, you know, they're being like icebergs. But these individual mountains don't have roots. So we know there's something strong down there, and that's the upper mantle. And in a craton, the mantle is very, very strong, whether it's wet or dry. However, if you add water, which is this dashed line, what you have in the crust here above the moho is a very weak zone right in here, right in the lower crust. What's happening there? You're taking things like pyroxene, like big framework minerals, feldspars, and you're turning them into micas, which are extremely weak. So we develop micas in there, and that's our slip plane. At least that's what I think. I haven't flown this through all the people in my project yet. I'm sure I'll get a little group. But this is new. But the idea being that it's really not heat developing these structures, it's the fluids. It's the fluids which are ungluing the mantle and the crust above, causing detachment. And creating, as I said, this jelly sandwich where the upper crust is strong to about 20, 30 kilometers, and then it's very weak, and then the mantle is very strong. So, this is all pretty new, so I just had to sort of band-aid some graphics here. This is your classic cordillera model by Hinman and others, also some stuff in press. You've got water coming off, weakening the mantle, creating from strong lithosphere to a asthenosphere, which circulates, you get melting, all that water is being pumped out of the system. Here, we have this low-angle slab. We don't have an arc. It's freezing the mantle above, and it's developing water. The water which is dehydrating is coming up, creating a weak zone, which allows the craton to detach and slide to the east. So that's the story. I think crustal detachment, such as we see here, the how, needs both compression to drive it and push from the west, and fluids to unglue it. So, this is the perfect audience, the perfect place to be talking about basement-involved structures like the wind rivers and the grow bogs being the same as the thrust belt structures, because here is where they actually come right together. And we're active at the same time, right here in Jackson. And it turns out the same sequence of deformation is going on. These basement-involved structures are a lot more variable. If you look at thin-skin structures, they're like sinusoidal waves, nice and regular, because they're nice regular beams of layers of strong material. In comparison, basement developed over billions of years with all sorts of foliations, weaknesses, strong zones, an amphibolite, a mafic rock, a granite would be weak because of the quartz, and thus we have a lot of reactivation of pre-existing weaknesses. And then why regionally? Well, you need two things. I think lower crustal fluid weakening is critical, and upper crustal shortening to drive the system. I also suspect that the penetrative shortening, the shortening throughout the crust, which occurs is probably sealing the fluid conduits and keeping the water from going down or getting up and escaping the lower crust. And so it may be a propagating thing where this fluid propagates. I think this is probably an analogous process to what we see in tremor and earthquakes on the west coast on a lot of these cordilleran orogenies, which are also fluid created. I'll leave you with a picture of what it's like to do field work in the Bighorns outside of Buffalo, and I'd love to hear some questions. Can everybody hear me?
No, everybody can hear it. You have a good voice.
Oh, okay, good.
Field voice.
I usually have such a big voice I have to turn it. Go.
That's for talking to your field officers. The fluid weakening, you've got water that's in the rocks and it's dehydrated. What percentage water is in that rock? Is it just a small fraction of percentage?
It's only about perhaps for an antigerite or some of these minerals, it can be up to 10%. Okay. In other ones, it can be 2-3% in a hornblende, which would be all the way deep underneath, 1,000 kilometers.
10%.
Right.
And so the fluidization that's weakening the rock, it's not actually a fluid floating lubrication type mechanism. It's changing the rock and making it weaker. Is that correct?
I think that's the case because what we know from thrust tectonics is that when we thrust a rock up, the friction usually creates a surface slope, an angle.
Yeah.
Just like when you push a snow shovel and you have the thing wedging up in front of your snow shovel.
Especially
And
if it's wet.
And if it's wet, actually it'll go out further sometimes because it's less friction. Here, we're going almost flat, so there has to be very, very little frictional coefficient there. And we're finding that to be the case, certainly in these tremor earthquakes on the west coast.
Can you extend your lower crustal fluid weakening model as far south as the upper Colorado Plateau?
Absolutely. Big question in the Colorado Plateau is, to me at least, Colorado Plateau is minimally deformed block which has deformation, the thin skin thrust belt to the west and the front range, everything else to the east. Does it have minimal deformation because it's attached to the mantle lithosphere? It could, and some of the faults may go through the mantle lithosphere there. Or it could be that the base of the crust is so weak, it's moving like a raft. So that's still something which needs to be looked at. Things do change over the border. Yes?
How come, like when I water the garden, the water goes down. How come the water wants to come up?
The water wants to come up because under that great pressure, the lighter material moves upwards. Okay? So when you put it in the garden, it's going into, basically it's displacing air and things like that. Here, you're pressing it. And it's just like, when you step on a balloon or, you're pressing cider. Okay, and making apples, you put the apples in there, you grind it down, you press it, that stuff's going to try to get out.
Like walking on wet sand. You step in sand.
Right.
Are these structures unique, or are there similar ones in Asia?
There are similar ones in Asia, and the interesting part is that there's very similar ones in the Tian Shan, right in the middle of Asia. Whether that's actually a reactivation of a big lithospheric transcending fault or detachment from the Himalayas is still not known. But one of the things which this suggests is that you don't really need to have low-angle subduction as much as just a source of fluids. So there's other origins, like the ancestral Rockies in Colorado, and which came all the way up here too in smaller amounts, about 300 million years ago. We don't have any low-angle subduction which we can link to that. Maybe we just had another source of fluid. It's a matter of what is the smoking gun here. Yes?
During Laramide time, the Atlantic Ocean was opening.
Right.
Which implies that the craton was being thrust over the Pacific, rather than the subduction zone being thrust under the craton. The craton was mowing the subduction zone down. And I wondered if you thought about, I mean, you've got an amazing set of data, it's incredible. But you thought about it from that point of view, because there's a little bit of a flip the way we use it.
And a lot of it's relative. Okay?
Did everybody hear the question in the back?
So the question is, are things being thrust over or thrust under? And does it make a difference? In terms of the mechanism for driving plate tectonics, it's pretty clear that it's the oceanic plates which literally fall into the mantle because they become denser than the mantle around them. What happens is the basalt turns into eclogite, which has garnet, which the mantle doesn't have so much of, and garnet is one of the densest minerals, and it acts like a sinker. So oftentimes things are moving relatively. Now, there's a lot of new work which suggests that all the actual crust is moving westerly. And that's why there's an asymmetry to these origins. What we see on the west side of the Pacific is very different from what we see on the east side of the Pacific. So there's a lot still working with that. There's not a lot of push involved from the spreading, because the spreading is pretty passive. You're cracking it open, and the only push from a spreading ridge actually comes from the slope. And the slope averages about 0.003 degrees. There's not a whole lot of push from that.
Yeah, I think in the 80s, that was very definitely the model. And what was thought was that the downgoing plate kind of skated down. Like when you have a paper towel in a bathtub and you push the edge, it'll skate down under the water. And so the thought was that what was driving plate tectonics was the thickening slab that was getting heavier as it went down, was skating down under the continent.
Right.
But for the Atlantic to open, that means that the slab is falling down vertically, not on a slope.
Yep, and that's correct.
And that it's the craton that's essentially helping push it down. Because you've got to get it down a certain distance before the eclogite really kicks in as a major force. So it's the concept that it's not the Pacific plate being pushed up against the North America, it's North America mowing down the Pacific plate.
That's actually correct, yes. I mean, and that's some new work is showing that the overall plate motion is, it's a lot of the questioning of the whole Yellowstone hotspot. Is it a hotspot? Is it really just a rift? Comes from, and some of the work from that is suggesting that our reference frame has been flawed. It's clear that the weight of the plates, the phase changes in the oceanic plate are what driving it, but whether there's also another torque involved is
It becomes a lot easier to understand thin skin tectonics if you're actually, you've got this little thin wedge of sediments up top, and the craton is being pushed westwards underneath it. Now you can have a little bit of deformation right at the edge, whereas if you're thinking of it originating from the west, then you've got to explain how this thin skin tectonics can propagate out because it doesn't have much strength to it.
We could talk more about this, but I think basically for an individual fault, whether it pushes this way or pushes that way, it's really not going to make a difference. Let me grab.
Does the water show, or fluids show up in the volcanic rocks in Wyoming? Like, can you look at them and go, oh yeah, there must have been water involved, or?
There's a lot of, particularly in Four Corners area, where they actually have xenoliths coming up. They show these xenoliths are highly altered. So there's a lot of water coming off of the slab, the Farallon slab, at that time altering them. Further out on the edge of this whole low-angle subduction area, we have kimberlites. And kimberlites are very enriched in fluids. That's how they get up there. They blast their way upwards from great depth, 200 kilometers, at least 100 kilometers, in order to have diamond in it. And so there are releases, yes, showing up. Yes?
Can you talk about the orientation of the creeks versus the other arches, which all seem to run in the northwest, and the Alleghenies and Rivers almost perpendicular?
Right. So the question is, why do we have these east-west arches like the Uintas? And maybe I can back up a little bit. Oops, I'm going the wrong way. Oh, the ones which didn't make it in, I could have been a lot longer. You're lucky. Let me just see. There. Okay, that's why I was holding this thing backwards. All right. So, for instance, the Uintas here are east-west. I consider that to be a knife into the foreland by the Cordilleran thrust belt, because you can take seismic lines from here right around to the north end of the fault, and you see the big thrust faults here, wrap in here, and go into basement. So this thing is like a knife which is being projected into the foreland, and it's utilizing an old ancestral Rocky Mountain, 300 million year old fault system, which created a graben there, which got picked up and thrust into the heart of the foreland. In the case of the Owl Creeks, which is right in here and is more or less east-west, we have a lot of, all the foliation there is east-west. There's a greenstone belt there. What happens here is, I think we develop these arches like the Wind Rivers, the Bighorns, the Beartooths. They're sort of on echelon. They're probably based on a weakness. Then you've got to link them together as things compress more. And in this case, we had basement weaknesses, the foliations, the layers in the rock, dead parallel to a nice zone which allowed this to wrap around. So in both cases, it's weaknesses. In this case, Precambrian weakness, or Precambrian crystalline rock weaknesses. Here it's probably this ancestral Rockies faulting, which is actually following this old Precambrian rift right in here. And back.
It sounds critical to the thesis is the angle of subduction, and is that what determines that angle? And relatively flat versus steep, and are they localized? Are they how localized are they? What determines the localization of them?
Well, here we have the Juan Fernandez Ridge, which is coming in. It's actually moving slightly obliquely, and these arches here started up here and moved out here, the Sierras Cordoba, right in this area here. One of the interesting things is this subduction zone. So these are the contour lines. So here it's uniformly dipping steeply in, and you have an ordinary subduction zone with the arcs. Here you have no magmatic arc. It's flattening out, which is the spacing between here, and then gets steep again. But it's still deforming out here. Why? Because it's not a function of the slab. The slab earthquakes are all basically due to the bending of the earth of the slab. It's probably just because it's kicking off water in this whole region here, which is ungluing the craton. That would be my guess.
The mechanics you've been describing here, the arches, the Bighorn, is that the same mechanism for Sheep Mountain west of the Bighorns and the Priors up north of the basin?
The Priors are a continuation of the Bighorns.
Okay.
Okay, Sheep Mountain is a smaller fold on the Bighorns. It's part of one, actually, a number of my restored sections showed it developing. But it's basically, you're squeezing the rock and it's actually a reactivated weakness there, because that moved in 300 million years ago during the ancestral Rockies too. And in fact, weaknesses are shown throughout that area of the Bighorn Basin, because at that time, we had the laydown of the Ten Sleep sandstone, which was the major oil reservoir for that area. And on top of these now existing large structures, the Ten Sleep oftentimes is missing. It never got laid down, because those were paleo highs. And so the Laramide came around, found those nice, greasy, mica-rich fault zones, moved them first. Yes?
So it's still moving, right?
Not now in the Rockies. We're actually splitting apart. That's a whole other thing we did in the Bighorns, is actually look at current day natural activity.
Okay.
And we found out we're really just part of the Basin and Range, part of what's happening here in Jackson, that we're splitting apart. Down in the Sierras Pampeanas, it is still moving, and it's important for us to understand why. Mendoza was shaken to the ground about 70 years ago, and they decided that that was not a good place to put a town, so they moved it to an area which hadn't shown, which is, if you understand earthquakes, that's just the area which is loading for the next earthquake. So it's important to try to understand these for that reason. So some of these are active, the Rockies are not.
So going to the snow shovel analogy, what at the edge of the snow shovel is just where the plates stop?
Well, that's sort of a thrust belt. If you ever want to do a thrust belt, just go out and push a snow shovel. A beautiful thrust belt.
Not for like the
Not really the subduction. That would be, basically this whole area out to the east here, and actually this whole region here. But the thing about this one is the Cordilleran thrust belt unglued the sediments. This one unglued at the Moho. We're very close to it.
But the whole thing moved so far east and then just went down or stopped? Or
I just stopped.
Just stopped, okay.
Yeah.
That's
At that point, it stopped right about the time when we were going from subduction to strike-slip faulting, which we currently have on the San Andreas Fault.
Are there any exposures anywhere in the Bighorns and canyons going through where you can see what your hypothesis is about the detachment, kind of where it comes up to the unconformity with Cambrian rocks?
We certainly see the
fluids, evidence of fluid flow there.
I'm still just looking into that now, okay?
Is that something
The idea is that this would be, the fluid weakening zone would be 30 kilometers below surface right now.
Right.
So we wouldn't necessarily see that. However, there are a lot of hydrothermal activity, things like that, which might have that character.
You might be able to find an exposure somewhere.
Yeah.
Or is it not deep enough?
If it's really not deep enough.
Yeah.
Yeah. The biggest structure here is the place to probably see it is in the Wind Rivers, because that's by far the biggest structure. It's probably got at least 30 kilometers of slip. So that could bring you up pretty close, but it's a pretty low angle slip.
Yeah.
It'll dip at about 30 degrees, so it's not going to still take that deep stuff up. Yes?
Was there a sinkhole in the Bighorns last summer, and what was the mechanism on that?
There is. Okay. The question was whether there is a sinkhole And there wasn't a sinkhole so much as a big slide. You know, basically these shales, again, when you have these shales, when they get very wet, they can slip. So there's a whole section of hillside which slipped and created these big fissures. And yeah, that was just gravity tectonics.
Is that fairly common in the Bighorn?
It's common everywhere in the Rockies.
Look over here.
Think about it. I'm sure Jackson is an epicenter for unstable mass motions. We call it mass wasting. Yes?
Can you show on the map exactly what you define as the Rockies?
Yeah, that's a real question, and I kept on flipping back and forth. The question is, what do I define as the Rockies? I tend to define the area here as the Cordilleran thrust belt, and this area is sort of as the U.S. Rockies. But then up in Canada, they call the Rockies their thin-skin thrust belt. So this would be, so I need to look into that, quite honestly, because there's a lot of mismatch. The reality is it's forming by the same stresses. The mechanisms and the depth of faulting is a little different. Yes?
It seems like you have a whole new theory here that's replaced a lot over the last half a century or so, information-wise. And I was wondering if in this process you've come across, like in my own work, I've noticed that there's an isosceles geometry amongst the tallest peaks. And is there anything that would indicate what would drive that in your work? Like, you know, like tallest peaks in Colorado all have these isosceles formations amongst the peaks?
You know, a lot of the tallest peaks in Colorado are there because they popped up on the sides of the Rio Grande Rift, just like the Tetons. So they are big rift structures with soft mantle underneath, a mantle pillow. They're not necessarily much thinner crust, but they're being very hot areas. You got Yellowstone, which is buoying up the whole thing. There is a lot of new thought on all of this stuff, from Yellowstone to the Rockies to Rio Grande Rift, but I think we're finally getting a good handle on it. Any more questions?